In this chapter, we'll be looking at differential equations, which are equations involving a derivative. Now, to solve a differential equation, this is going to mean that we want it to be y equals whatever it is that we're looking for. We're also going to use the fundamental theorem to solve an initial value problem. This is very similar to something that we did last chapter. In our first example, we want to solve the differential equation. So, as I said here, we want to make a differential equation equal to y. Now to do that, since we're given this as dy dx is equal to this, that's what makes this a differential equation. If I want to work backwards to get an antiderivative, I'm going to take an integral, and I can do that to both sides. An integral means to take the general antiderivative, so the antiderivative of secant squared would be tangent of x, 2x would be x squared, 5x, and since it's a general antiderivative, we would include plus c. So it's solved because y is equal to everything else. In this next example, we're given an exact value. We don't want the general solution with plus c. We want to know what c is. So we're going to start in the same way by taking an antiderivative of each side. Antiderivative dy dx is y. E to the x is its own antiderivative, 2x cubed. And then we have plus our constant. Now we need to find that constant. We're going to do the same as we did before. We're just going to plug in this point 1, 0. So when y is 0, x is 1. To solve that for c, we're going to get c is equal to 2 minus e, which is a constant. We don't need to get a decimal value, and we can leave it as an exact value. And so our final answer will be y is equal to e to the x minus 2x cubed, plus we plug in our c, 2 minus e. In this example, we're going to see a case where there's a discontinuity in our graph, and we're going to see what to do with that. First of all, let's look at our antiderivative here. So dy dx, and then plus a constant. Now, using our initial value, we can plug that in, plugging in 0 for x, which is going to give 0. Tangent of 0 is going to give us 0. And our y value in x is 0 is 3, meaning we have a constant value of 3. And so we can plug that in and get that equation. Now on first glance, that looks okay. But if we look closer at this graph, we're going to see a problem here with the tangent of x. And that problem is based on the graph of the tangent of x. This is actually the whole graph x squared minus tangent of x. But remember that the graph of tangent of x has vertical asymptote lines in it, which means there's a jump discontinuity or an infinite discontinuity at negative pi over 2 and at pi over 2. And every pi units after that, we're going to get another discontinuity like that. Now our problem is when we're looking at an antiderivative, we're starting with this equation right here, which is telling us our slope at any given point. So what this is telling us as I move from left to right is, okay, if I'm right here, then I know that my slope is about like that. If I go here, it's about like that. If I know it's here, it's about like that. At 0, I have a slope of 0. Maybe here I have a slope of -1, and so on. And so it tells me as I move from left to right how far I need to move to get to the next point, because that slope is changing. We're moving in small increments, and so we know what that graph will look like. The problem is when we jump over an asymptote line, since there's a discontinuity there, we don't know if we continue using the same pattern. Maybe this gets moved down here, or moved down here, or moved down here. We can't keep following, like connecting the dots as we would on this side. Same thing when we move back to this side over here. I jump. I don't know how far I jump, so maybe I need to be over here instead. We don't really know. So any kind of discontinuity in our graph means that we have to add a restriction, a domain restriction. What this is telling us then is I have to ignore this part of my graph, and I have to ignore this part of my graph. I was given an initial point between negative pi over 2 and pi over 2. Since those are the points where the discontinuity is, I can't jump over here. If my initial point was somewhere else, let's say that my initial point was right over here, well then I could have started here, but then my domain restriction would be between these two asymptote lines. And so our answer to this one is really this equation that we found on the last page, plus we must state this restriction right here, that this is only valid from negative pi over 2 to pi over 2. In this next example, we're going to need to take an antiderivative just like the other ones. I notice our variable this time is u, so I'm actually going to be using the integral with du on here. But what we need to do to take an antiderivative, there's a bit of a trick here. Notice that we have this sign of u inside of something that's raised to the third power. What we should suspect in this case is that maybe the chain rule was used to get here. And so we want to look at what's inside of a more complicated function. So we want to look at a function that's inside of another, which would be the sine u. We could think of this as being 4x cubed, and then there's something else after that. Notice if I took the antiderivative of this, it would be x to the fourth. Now if we're thinking of this in terms of the chain rule, then maybe where that came from was if I had the fourth. Now let's think about what that would leave in here. If we were using the chain rule, that would mean we started with sine of u to the fourth power. To take the derivative, we would multiply by the exponent and subtract the exponent by 1. That's what we have. And then the chain rule would cause us to multiply by the derivative of the inside, which would actually give us this cosine of u here. So if I take the derivative of this, just to check our work again, that would give me 4 sine of u to the third times the derivative of the inside, which is cosine of u. So this right here is our antiderivative. Now since it's a general solution, we're also going to add a plus c on there. We will be learning a more systematic way of doing that that'll make these a little bit easier, but that comes later. In this next group, we want to fill in the blank. If I want this to equal 0, remember that we would have to have a 3 here. This is something we did last chapter. We're just building on it some more. If I want to go from 0 to x and get 0 when x equals 3, then I would put a 3 down here. Same thing, if I want to do it when x is negative 4, I would have just put the negative 4 down there instead. That way when I plug in negative 4, it would go to 0 again. This one down below, we want to get y equals 3 when x equals negative 2. So we'll be looking at this when x is negative 2. That'll force this first part here to be 0. I want y to be equal to 3, so all I have to do is add 3. Okay, so again, this first part is integral. If I'm going to negative 2 when x is negative 2, that'll give me 0. I add 3 to that so that I get the y value I want. In this problem, they ask us to find the solution to this differential equation. Okay, now we don't know how to take the antiderivative of this, but we can still write it in terms of an integral. We want this when x equals 7, and we want to get y equals 3. So I want when x is 7, so 7 to 7 is going to give me a 0 here for this whole integral part, but we want it to be equal to 3, so I'm just going to add a 3 there. And now when I plug in 7 to 7 be 0, plus 3 equals 3. So here's my answer right here. In this next example, we're asked to find a general solution to dy dx equals cosine of x. Now don't get this confused, we're going to be doing something different next lesson that looks similar to this problem. But what I want you to see right now is if we take the antiderivative of cosine, then that's going to give us sine. They're asking for a general solution, so what we're looking at is if I had sine and it was plus 0, it might look like this curve right here. But since this is plus c, then that means that we could have taken that and said maybe plus 1 or plus 2 or plus 3 or wherever that is, it can move up or maybe subtracting our constant depending on where we've put our initial point. Okay, maybe they tell you that the initial point is somewhere over here. So we would just take our graph and we would move it to make sure it passes through that point. What this is really doing for us is if we look at this cosine function, if we think about plugging in different values of x, for example, if I plug in x equals 0, then I know that the cosine of 0 is 1. Notice here at 0 I have a slope of 1, and I will have a slope of 1 no matter where I go, no matter how far I move that up or down. At pi over 2, cosine of pi over 2 would be 0. Notice I have a 0 slope. Same thing with negative pi over 2 or 3 pi over 2. I'm always getting that 0 no matter how far up or down I move. Or maybe here at pi I have a negative 1, a negative 1. Same thing back here at negative pi. And so as we plug in these values to this, these are my slope values, And we can see as we move it down, it will always give us this function here, and we can see that based on the slopes.